Semiconductors are a class of materials that are critical to the operation of modern electronics. They have revolutionized the way we live and work, enabling the development of everything from computers and smartphones to solar panels and electric cars. What are semiconductors? A semiconductor is a material that has electrical conductivity somewhere between that of a conductor and an insulator. Conductors are materials that allow electric current to flow easily, while insulators are materials that do not allow electric current to flow. Semiconductors are unique because they can be used to control the flow of electric current. This property is what makes them so useful in electronics. The most common semiconductor material is silicon, which is used to make integrated circuits, ICs, that form the basis of most modern electronics. Other common semiconductor materials include germanium, gallium arsenide, and indium phosphide. These materials are chosen based on their electrical properties and their ability to be formed into the desired shapes and sizes. How do semiconductors work? The electrical properties of semiconductors are determined by their atomic structure. Semiconductors are typically made up of atoms with 4 valence electrons. Valence electrons are the electrons in the outermost shell of an atom that are involved in chemical bonding. In a semiconductor material, these valence electrons are shared between neighboring atoms, forming covalent bonds. At low temperatures, these covalent bonds are very strong, and it is difficult for electrons to move around the material. This makes the material behave like an insulator, with very little electrical conductivity. However, at higher temperatures, some of the covalent bonds can be broken, freeing up electrons to move around the material. This increases the electrical conductivity of the material. Semiconductors can be further manipulated by adding impurities to the material. This process is called doping, and it is used to change the electrical properties of the material. When an impurity is added to a semiconductor material, it can either donate or accept electrons. This creates regions of the material that have an excess of electrons, N-type, or a deficit of electrons, P-type. These regions are called dopant regions. When a P-type and an N-type material are brought together, they form a p-N junction. At the junction, the excess electrons in the N-type material combine with the holes, deficit of electrons, in the P-type material. This creates a depletion region where there are no free charge carriers. This depletion region acts as a barrier to the flow of electric current, which makes the p-N junction useful for controlling the flow of electric current. Why are semiconductors important? Semiconductors are critical to the operation of modern electronics. They are used to make everything from microprocessors and memory chips to transistors and solar cells. Without semiconductors, many of the devices we rely on today would not be possible. One of the most important applications of semiconductors is in the field of microelectronics. Microelectronics involves the design and manufacture of ICs, which are used to control and process electronic signals. ICs are used in computers, smartphones, televisions, and many other electronic devices. They are made up of millions of transistors, which are tiny devices that can be used to switch electronic signals on and off. Transistors are made from semiconductor materials, which is why semiconductors are so important in the field of microelectronics. Another important application of semiconductors is in the field of photovoltaics. Photovoltaic cells, also known as solar cells, are used to convert sunlight into electricity. There are two main types of semiconductors: intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are pure semiconducting materials. while extrinsic semiconductors are doped with impurities to change their electrical properties. Intrinsic semiconductors are pure semiconducting materials, such as silicon and germanium, which have their own intrinsic properties. These materials have a balanced number of electrons and holes, and at room temperature, their electrical conductivity is relatively low. However, when these materials are heated or exposed to light, some of the covalent bonds are broken, freeing electrons and holes to move through the material, resulting in increased electrical conductivity. Extrinsic semiconductors are doped with impurities to change their electrical properties. There are two types of extrinsic semiconductors, N-type and P-type. N-type semiconductors. N-type semiconductors are doped with impurities that have one more valence electron than the semiconductor material, such as phosphorus or arsenic. These impurities create excess electrons, which can move freely through the material, creating a negative charge. This results in an increase in electrical conductivity. P-type semiconductors. P-type semiconductors are doped with impurities that have one less valence electron than the semiconductor material, such as boron or aluminium. These impurities create holes or positive charges in the material, where electrons are missing. These holes can move freely through the material, creating a positive charge. This also results in an increase in electrical conductivity. The P-type and N-type semiconductors are used together to create a p-n junction, which forms the basis of many electronic devices, including diodes, transistors, and solar cells. In a p-n junction, the N-type and P-type semiconductors are brought into contact, and the excess electrons from the N-type semiconductor combine with the holes in the P-type semiconductor, creating a depletion region. This depletion region acts as a barrier to the flow of electric current, which can be used to control the flow of current in electronic devices. In addition to these types of semiconductors, there are also compound semiconductors, which are made up of two or more different elements. These materials have unique properties that make them useful in a variety of applications. For example, gallium arsenide is a compound semiconductor that has a higher electron mobility than silicon, which makes it useful in high-frequency electronic devices such as microwave amplifiers and high-speed transistors. Overall, semiconductors are essential materials for modern electronics, and the different types of semiconductors, intrinsic or extrinsic, N-type or P-type, and compound semiconductors, offer a wide range of properties that can be tailored to specific applications. The VI characteristics of a semiconductor describe the relationship between the voltage, V, applied across the material and the current, I, flowing through it. The VI characteristics of a semiconductor depend on its type, doping concentration, and temperature. Intrinsic semiconductors have a nonlinear VI characteristic. At low voltages, there is very little current flowing through the material, but as the voltage increases, the current also increases rapidly. This is due to the generation of electron-hole pairs in the material, which increases the number of charge carriers and allows more current to flow. However, the VI characteristic eventually levels off at higher voltages due to the saturation of the charge carrier density in the material. Extrinsic semiconductors, N-type semiconductors. The VI characteristic of an N-type semiconductor is similar to that of an intrinsic semiconductor, but with a higher current density due to the presence of excess electrons. The VI characteristic of an N-type semiconductor is also nonlinear and increases rapidly with voltage, but eventually levels off due to the saturation of the charge carrier density in the material. B. P-type semiconductors. The Vi characteristic of a P-type semiconductor is also nonlinear, but the current density is lower than that of an N-type semiconductor due to the presence of holes. At low voltages, the current is low because there are few free charge carriers, but as the voltage increases, the current increases more rapidly due to the injection of electrons from the N-type material. Eventually, the Vi characteristic levels off due to the saturation of the charge carrier density in the material. P-N junction. When an N-type semiconductor and a P-type semiconductor are joined together to form a P-N junction, the Vi characteristic becomes asymmetric. At low voltages, the current is very low because the depletion region acts as a barrier to the flow of charge carriers. As the voltage increases, the depletion region becomes narrower and the current begins to flow more easily. When the voltage exceeds a certain threshold, called the breakdown voltage, the current begins to increase rapidly and the P-N junction becomes damaged. Overall, the Vi characteristics of semiconductors are important for understanding how they behave in electronic devices. The nonlinear nature of the Vi characteristics of semiconductors allows them to be used in a wide range of applications, including diodes, transistors, and solar cells. By controlling the doping concentration and temperature of semiconductors, it is possible to tailor their Vi characteristics to specific applications. Semiconductors offer several advantages and disadvantages, which are discussed below. Advantages. Small size. Semiconductors can be made very small, which allows for the creation of small and lightweight electronic devices. Low power consumption. Semiconductors require very little power to operate, which makes them ideal for use in portable electronic devices. High speed. Semiconductors can switch on and off very quickly, which makes them ideal for use in high-speed electronic devices, such as computer processors. High reliability. Semiconductors have a long lifespan and are not subject to wear and tear like mechanical devices, which makes them more reliable. Customizability. The properties of semiconductors can be customized by varying the doping concentration, which allows for the creation of materials with specific electrical properties. Disadvantages. Cost. The process of manufacturing semiconductors is expensive, which makes electronic devices that use semiconductors more expensive than those that use other technologies. Fragility. Semiconductors are fragile and can be easily damaged by electrostatic discharge or mechanical stress. Environmental impact. The manufacturing process for semiconductors can have a significant environmental impact, as it involves the use of toxic chemicals and generates large amounts of waste. Limited temperature range. Semiconductors have limited temperature ranges, and their electrical properties can change significantly with temperature, which can be a problem in certain applications. Limited voltage range. Semiconductors have a limited voltage range, and exceeding this range can cause permanent damage to the material. Overall, the advantages of semiconductors outweigh their disadvantages in most applications, which is why they are widely used in modern electronics. However, ongoing research is needed to address the environmental impact of semiconductor manufacturing and to improve their performance in extreme temperature and voltage conditions. Semiconductors are used in a wide range of applications, including electronics. Semiconductors are the foundation of modern electronics, including computers, smartphones, televisions, and home appliances. Solar cells. Semiconductors are used in the manufacture of solar cells, which convert sunlight into electricity. LEDs. Semiconductors are used in the manufacture of light-emitting diodes, LEDs, which are used in lighting and electronic displays. Transistors. Semiconductors are used in the manufacture of transistors, which are used in amplifiers, switches, and other electronic devices. Sensors. Semiconductors are used in the manufacture of sensors, including temperature sensors, humidity sensors, and pressure sensors. Medical devices. Semiconductors are used in the manufacture of medical devices, including implantable medical devices and diagnostic equipment. Automotive. Semiconductors are used in the manufacture of automotive electronics, including engine control modules, anti-lock brakes, and airbag systems. Aerospace. Semiconductors are used in the manufacture of aerospace electronics, including communication systems, navigation systems, and satellite components. Defense. Semiconductors are used in the manufacture of defense electronics, including radar systems, missile guidance systems, and communication equipment. Overall, semiconductors have become an essential part of modern technology and have revolutionized the way we live and work. As technology continues to advance, the demand for semiconductors is expected to increase, driving further innovation and development in the field.